So find your notebook. This lesson is Unit 5, Lesson 5. Our essential question today is how do I write equations for exponential functions? And you'll need this it's a full sheet, folded in half, and we're going to take notes on here today. So go ahead and pause the video to get all this down. The table of contents, by the way, you can just write equations for the table of contents. So go ahead and pause, get this down, and then unpause. So example 1 says Hector buys 3 drinks at roast this month. He quadruples the number of drinks he buys each month from here on out. That's a pretty intense coffee habit. So quadruples, think for a minute about what that means. And hopefully you realize it means times 4. So it says let x equal the number of months and let f of x equal the number of drinks. So this month, we're starting at month 0. He buys 3 drinks. I want you to go ahead and pause the video and see if you can fill out the rest of the table. If he's quadrupling each month, what would the rest of the table look like? And then press play when you're ready. All right. So hopefully you have this filled out correctly. We're just multiplying by 4. 4 is the common ratio here. And then go ahead and again kind of pause the video and take a minute to fill out the graph. I want you to label the x-axis, label the y-axis, and do your very best to approximate where the points go. Then press play when you're ready. The x-axis is the number of months. The y-axis is the number of drinks. 0, 3, so it skips from 0 to 50. So 3 is like way down there. And then we've got 1 and 12. That's like 25 is halfway up, so we're still really far down. 2 months is 48, so that's almost at 50. And then 3 months is 192, which is almost at 200. So you can see it really explodes. So it's going to go, whoops, I missed. Something like that is the graph. So this is the graph of an exponential function. Now to write the equation, this is really key. The basic form of an exponential function looks like this. Y equals a times r to the power of x. A is the start value, and r is the common ratio, or you'll hear me call it a lot the growth rate. So this is where we're starting. You can think of it as like the y-intercept. And this is the growth rate. So I'd like you to try, even though we haven't done any examples like this, I want you to try to write an equation for Hector's roast obsession. So pause, see if you can write the equation, and then when you're ready, continue the video to see if you got it right. So Hector's start value was 3 because this month he had 3 times our common ratio or our growth rate, which in this case is 4. So it's times 4 every month. And then x is our exponent. So this is what your equation would look like. And equations are fabulous because now part A says how many drinks will Hector, that should say buy in the 10th month. Show your thinking. So before, we would have had to keep this table going all the way down to 10 and keep going times 4, times 4, times 4. But now we don't have to do that because we have this lovely equation. So we're going to write y equals 3 times 4 to the power of x. X stands for the months here. So all I have to do is put that 10 in where the x is. Y equals 3 times 4 to the 10th power. And our calculators can do this for us. It's important that you know how to type it in. So you're going to do the 3, and I'm going to write it exactly as it is on my paper. Parentheses, your calculator knows that means times 4. And there's no 10th power button on your calculator, but there is an exponent button. It's under the pi key. It's right here. This means to the power of. So you're going to hit to the power of 10. And we have our answer. So according to this problem, in the 10th month, Hector will buy over 3 million cups of coffee. So let's go ahead and write that number down. So this is a much easier way of kind of figuring out what's going to happen in the future than continuing to go times 4 times 4 times 4 times 4 times 4. Now, there's this end behavior stuff. The end behavior means what happens basically if this goes on forever, right? How many drinks will Hector buy after infinity months? If this continues forever, then how many drinks will Hector end up buying? And the answer, of course, is it's going to keep getting bigger and bigger and bigger and bigger all the way up to infinity. So he's basically going to buy infinity cups of coffee. Of course, this is not realistic. This is some fancy notation for end behavior. This reads, as x keeps going on and on to infinity, okay, these are the inputs, then f of x, which is our outputs, are also going to go to infinity. In other words, as this keeps going forever, right, all the way out to infinity months, then the output, the cups of coffee, will reach infinity. This is really confusing. We're going to keep coming back to it. If it's not making full sense right now, don't worry. That's okay. So go ahead and open this up, and we're going to begin taking notes on the inside. So we're looking at example 2 now. Go ahead and read the example to yourself. Underline what you think is important. So this is a different kid who goes to roast, but instead of talking about months and coffee, it's months and money. So it says Noah starts off the year with $300. So go ahead and put $300 on the table where you think it goes. And each month he spends half of his money on coffee at roast. So X is the number of months and Y is the amount of money that Noah has left. So if he's spending half of his money, we want to think about this rule because it's an exponential function as a times rule. So what are we multiplying by if we want this to be half, right? And I hope you can figure out that R has to be 1/2 here, or 0.5, right? Because he has a half of his money left. So if we multiply this by a half, we should get half of 300. And so we want to multiply by, 0.5 as we go down. 0.5, 0.5. By the way, that's the same thing as dividing by 2. But because this is an exponential function, our rule has to be a times rule. It can't really be a divide by rule. So it's just that we're multiplying by a fraction or a decimal. So I'd like you, using your calculator, to go ahead and fill out these 3 rows, multiply by 0.5, multiply by 0.5, multiply by 0.5. Pause if you need to. So we can see here that if he keeps spending half his money at roast, after 3 months, he'll only have $37.50 left out of the 300 that he started with. So this is the amount of money he has left. Let's go ahead and sketch this graph. Take a moment and label the X and Y axes. You can use this to help you. And once you have that done, please graph those 4 points. I'll do it up here, but it's probably better if you can do it on your own and then look up here to see if you did it right. So 0 months, $300 is the place to start here. Okay, so pause if you need to, but if you have this done, make sure yours look something like mine. I want to think about what's going to happen at months 4 or 5, even though my table doesn't go that far down, because we have room on the graph. I think it would be interesting to think that through. So will you take a moment? I'm going to just wait. Take a moment and extend the table, so times 0.5 times 0.5, and then let's see what it would look like to graph them. This gets harder and harder to graph, but we know like halfway between 0 and 50 is 25, so 1875 would be lower than that. And then, it's going to keep getting smaller. I want you to think about if this will ever become negative. Like if he keeps spending half his money, eventually he'll be out of money, but he's not ever going to, like, it doesn't say he uses a credit card, right? It's not like he's going into debt. It's just that his money is going to basically be gone eventually. So this graph is going to look something like this, where it's going to just get closer and closer to zero until it basically hits zero. It never actually will hit zero. If I keep dividing by two, I'll always have a little something left, but it'll be less than a penny, right? Which is basically zero. So that's what this graph is going to look like. It will not go into the negatives. Let's think about how to write an equation. So again, you might want to write, I'm going to use y this time. Y equals a times r to the power of x, where a is the start value and r is the growth rate, or the common ratio. And I know you've written this, but the more you write it, the more it'll kind of stick with you. So I want you to take a moment, I'll just wait, and I want you to write the correct equation for Noah's situation here. I'm still waiting. Okay. So you should write y equals the start value. Well, start value is always going to be matched up with 0, right? That's the start value. So at 0 months, Noah's got $300. So that's the start times the growth rate, or the common ratio. We already figured out that to get from one output to the other, we're multiplying by a half, or by 0.5. So here, the growth rate is 0.5. And then x is our exponent. So that's the correct equation here. So we're going to use that lovely equation to answer these questions, or I guess this one question. The question is, how much money will Noah have after 12 months? It's probably not going to be a lot of money, right? Because after 5 months, he already went from $300 to $9. So I think after 12 months, he's not going to have much left. But let's figure it out. Months is x in our equation. And so all we have to do is come back up to our equation and replace that x with 12. So let's do it. Y equals 300 times 0.5 to the 12th power. And I want you to practice typing that into your calculator to see what you get. And if you need more time, go ahead and pause so you don't get frustrated by me giving you the answer. But this is what I got. And that's exactly how I typed it in. When thinking about how much money this is it like 73 cents or like what, right? We have to think about how much money this is. And so with money, we usually really only look at like 2 digits after the decimal, which would mean that. So it's $0.07. This is like beyond a penny. And since that 3 is less than a 5, we wouldn't round up. So I would say this is approximately equal to, you could write it as $0.07, or you could just write 7 cents with the little cent symbol. Okay. So he went in a year, if he really spends half his savings every year at roast, which is, don't do that, that's ridiculous. But if you did, after a year, you'd only have 7 cents left of your savings. So back to this really confusing part, the end behavior. The question is, how much money will Noah have after infinity months? So imagining that Noah lived forever and he continued to do this for the rest of his life, how much money would he have? And so I hope you can see that eventually he would have nothing left, right? Not exactly nothing, because he would have some infinitesimal part of a penny left, but basically nothing. And so what you would want to say here is he would have no money left, something like that. I'm not too worried about this this stuff I'm much more worried about if you can explain what's going to happen if this goes on forever, but I do want you to see this. So this means as x goes to infinity, right? So if this continues forever, y, or the output, in this case, his money, would eventually become basically zero. So let's look. We have 3 more examples to do together, and then you're done with notes for today. And these are just graphs. We're specifically focusing on features of the graph, like where's the y-intercept. All exponential functions do this thing where it levels off at some point. So if we look, it's harder to see here, but this graph kind of would level off back here. This graph levels off to 0. Exponential functions explode in one direction and level off horizontally in another. And so that's what we're going to be focused on here. Some of this stuff you're already going to know, and some of it we're going to need to talk about a bit. So the y-intercept is the same thing as with a linear function. Where does the function cross the y-axis? So this is x, this is y. So you just kind of travel along until you find the spot. And in this case, the y-intercept, hopefully you can see, is 0. The asymptote. This, it's not a bad word. It's asymptote. That's a word you have not heard before. So asymptote means basically the boundary line. The boundary. This graph is coming up, 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 and then it's leveling off, leveling off, leveling off until it's basically flat. And so what we're going to do is draw a dashed line at the boundary, like where does it level off? And that boundary in an exponential function will always be a horizontal line left to right. So that happens when y is 1. And so the equation of the asymptote is y equals 1, because all of these points along here are at y equals 1. I know this is confusing, but we'll keep practicing it. Increasing or decreasing, so that's just asking as we travel along our graph. Just like with lines, we read exponential functions left to right. So as we go from left to right, is it going up or is it going down? And I hope you can see here that it's going up. It eventually levels off, but it actually keeps going up. So this is increasing. Increasing means going up. The end behavior here, as x goes to infinity. So again, that means follow your graph from left to right, and we might even write left to right, left to right. If this goes on forever and ever and ever, what happens with y? And in this case, it's leveling off. The question is, what is it leveling off at? So as we go from left to right, we're leveling off right at the asymptote, which is at 1. So y is getting closer and closer and closer to 1. This means as x goes to negative infinity. So this means if we go from right to left, okay, if we go backwards, negative infinity. This is negative infinity back here. This is positive infinity. So as we go backwards, what's happening? Well, if we go backwards, our graph is shooting downwards. Shooting down, and it's going to keep going down forever. And so that's going to head down to negative infinity. So in the y direction, we have positive infinity up here and negative infinity down here. I'm aware this is really confusing. Just stick with me. The domain here is going to be all real numbers, and that's going to be the case for, that symbol means all real numbers, but you can write it out too, all real numbers. That's going to be the case for every exponential function because it's going to go left forever and it's going to go right forever. It just keeps going in both directions. But the range is different here. The range, if you'll remember, is all of the y's. So the y's here don't go forever in both directions. So we're talking about how far up and down does our graph go. And you can see that it does go down forever, but it does not go up forever. This asymptote is like a boundary that the graph cannot cross. And so all of the y's in this graph are going to be underneath this asymptote. And so the way we're going to write that is we're going to say all of the y's are going to be less than 1. And this just means basically 1 is the boundary of our graph. All the y's are below that. Again, really confusing. It'll get easier with practice. Let's look at example 4. The y-intercept of this graph, you guys write down what you think it is. -2. The equation of the asymptote. So where does it level off? So here it's exploding up, but on the other side it's leveling off and becoming flat, and that happens right here. So the equation of that line is y equals -3, because the leveling off place is where y is -3. Increasing or decreasing. So as we go left to right, this graph is going down, right? Down. It eventually levels off, but it keeps going down. And so this graph is decreasing. Let's do this really weird end behavior stuff. As x goes to infinity, infinity is out this way. So that just means as we go from left to right, what happens to y? So it's leveling off, but where is it leveling off, right? It's leveling off at our asymptote, -3. As x goes to negative infinity, we're going backwards. So as x goes to negative infinity, it's exploding, but this time it's exploding up. Here it was exploding down. This time as we go backwards, it's exploding up towards infinity. And so we would say y goes to infinity. And this is backwards from right to left. The domain is all real numbers. That symbol stands for all real numbers because it goes left forever and right forever. Domain are all the x's. Range are all the y's. So the range here is not everything. It does go up forever, but it doesn't go down forever. This is the boundary. The graph will never go below -3. And so what we would say here is that all the y's, this time they're above -3, right? They're greater than that. And so we would say all the y's are greater than -3. I promise with practice you will get this. So for this last example, I would really like for you to try to do the whole thing on your own. If you're just copying down what I'm writing, you're probably not learning this very well. So take some time. I want you to pause the video. I want you to try to do the whole thing, and I don't even care if you make mistakes. I just want you to put something in each spot. So pause it, fill it out, and then when you're ready, press play. Press play and see if you got it right. So the y-intercept here is -3. The asymptote, the place where it flattens out, happens right here. And that happens at y equals -4. To figure out increasing or decreasing, you always want to go from left to right. So in this case, it's going up. So this is an increasing graph. For the end behavior, as x goes towards infinity, so that means as we follow our graph from left to right, y is exploding upwards, and it's going to go all the way up to infinity. As x goes to negative infinity, so that means as we read our graph from right to left, it's leveling off. And it's leveling off right at our asymptote at -4. So y eventually will head almost to -4. The domain is all real numbers, and the range here, our y's go up forever, but they don't go down forever. They're stuck right here. They can't go below this line. So all the y's on this graph are above or greater than -4. So if you were able to get all of that right, or even most of that right, put a big smiley face there. If you didn't, that's okay. It's a process, and I know it's hard without me there. We'll continue practicing this. So right now, I need you to do a couple of things. I think it would be really helpful if you could write out a couple of questions in the left-hand column here. I'm not there with you today. So what's confusing? What are you not sure about? What questions do you have? Write a couple of questions here, and then I'll be able to address those questions next class. And then obviously the most important thing is I need you to write a summary. Now, I would prefer you to do your summary in your notebook, but I also need you to type your summary into Google Classroom. So the same link as this video, there's a spot for you to type in your summary, and I'm going to be grading that over the weekend. This is just the way I know you watched the video and you learned something. So your summary, I think what it says in the link is it should talk about how to write an equation for an exponential function. So how do you write it? What are the different pieces of it? And that goes back to this. But then I'd also like for you to say something that you learned about the graphs of exponential functions, and it can really be anything. So just pick something that you learned about these graphs, maybe the shape of them or something about the infinity business. So what did you learn about graphs and how do you write an exponential function? So it's really best if you can write it here and then type it into Google Classroom, and I'll be able to get it graded over the weekend. And as soon as you're done with that, you can begin your homework, which I believe, let's see, I have it here, is on page, where is it? Page 9. Okay, so page 9 is your homework for today. It looks like this. Do the best that you can.